Okay, so here we're going to introduce the matrix multiplication. Right, up to this point we've kind of took us a while here to get to just matrices and matrix multiplication, and the idea is here is that we build as much as we can using kind of linear combinations here, so we can kind of see here the goal in doing that, right, is to think of our matrix multiplication, and why it's defined in this way is through these kind of linear combinations of vectors, column vectors, and scalars here. So if you see the definition here, all right, suppose A is an m by n matrix, and B1 through Bn, so those are vectors through Bp, excuse me, are the columns of an n by p matrix. Then the matrix product of A with B is the m by p matrix, where column I is the matrix vector product ABI, right? And symbolically is what we see here, right? AB is A times, we think of it, in the previous video we looked at the matrix vector product. Well, the matrix multiplication is just doing that repeatedly for however many columns of the matrix B we have, right? Now here notice that the size of the matrices is important in the sense that they don't necessarily have to be equal, right? As we'll see, when matrices are square, it makes things a lot easier. The multiplication, right? We don't have to worry about is this valid or not, but that's not always the case. Okay, here we notice that A is m by n and B is defined as n by p, so not the same size, right? What is going to be important in order for it to work is that if that n, notice they do have in common. So let's switch over here and let's talk more about that. Okay, all right. So here in our theorem there, okay, so in our theorem here, we have A to be this m by n matrix, and B to be this n by p matrix, right? And then the product AB, right, is this m by p matrix. Okay, so the way you want to think of this is when you multiply this out is that here the columns of the matrix on the left need to equal the rows, of the matrix on the right. Right? And the resulting matrix will be of size that has the same rows of A, but the P columns, right? The columns that are in the matrix B. Okay, so let's work this out with an example here, right? So let's say that we define A to be the matrix 1, 2, 3, -2, -1, -5, and then the matrix B to be this matrix, which we'll call 1, 1, -1, -1, 2, -3, 4, -5. Okay, and again in the definition here, those vectors B1, B2, B3, and B4. Okay, so matrix A is a size 3 by 2. Matrix B is a size 2 by 4. Right, where our P here is 4, right, the number of columns. So we have 4 column vectors of size 2 by 1. Okay, and we notice here, right, just from our definition, right, those two inner numbers need to match up, right? Number of columns in matrix A must match number of rows. So the resulting matrix AB, right away, I know is going to be a matrix of size 3 by 4, right? These outer numbers there. Okay. Now, in terms of symbolically what that product AB looked like, right? So AB, right, is the matrix A, which is 1, -2, 2, -1, 3, -5, times the first column, 1, 1, right? So again, we interpret it as the matrix vector product, and we kind of concatenate it, right, with the next product here, which will be 1, 2, 3, negative 2, negative 1, negative 5. And then the next column there, vector, would be negative 1 times negative 1. All right, and then moving along here, you get 1, 2, 3, negative 2, negative 1, negative 5. We get negative, or excuse me, 2, negative 3. And then here, the last one here is 1, 2, 3, and then negative 2, negative 1, negative 5, and then the last one being 4, negative 5. Okay, so we have that. All right, so that'll be our matrix AB. Now to do the calculations, again, looking at this, excuse me, from the previous video, we talked matrix vector product, right? We interpret this as 1 times the column vector here, 1, 2, 3. And then we add that to 1 times the column vector, negative 2, negative 1, negative 5. Right, and that gave me the column vector negative 1, 1, negative 2. Okay, so in my product AB, that would be my first column of here, negative 1, 1, negative 2. Excuse me. All right, and then the second column would be doing that second matrix vector product where we had, right, negative 1 times 1, 2, 3. And then also negative 1, so our minus 1 of negative 2, negative 1, negative 5. All right, and adding that together, we get 1, negative 2, excuse me, negative 1, and 2. So that would be my second column. All right, and then continuing this, doing the third and the fourth one, you should receive the result 8, 7, 21, and then 14, 13, 37. Right, and we have the required product here with the correct size 3 by 4 matrix here. All right, so that's one way to interpret that, as thinking it of a linear, the matrix vector product between that matrix A and then the column vectors that make up the matrix B. All right, that's one mode of interpretation. Now, another algorithm that is, I think here, useful to think about here, if we go back to our product here, all right, so here there's also another way to approach this. So if we have matrix A to be 1, negative 2, 2, negative 1, 3, negative 5 here, and then matrix B, 1, 1, negative 1, negative 1, 2, negative 3, 4, negative 5. Okay, now this is called kind of a row times column, right? Almost like a dot product between the row and the column here, right? So what I mean by that is, what I want to do here is I want to interpret this is I'm going to multiply this row and this first column, right? Like I would my dot product essentially, right? Where I take 1 times 1 plus negative 2 times 1. And what that's going to be my first element in my matrix. So this is going to be equal to negative 1. All right. So that gives me my first element. And now what I'll do next here is I'm going to keep working in this first column. Now to get the next element in this first column, the second row in that first column is now I'm going to move on to my second row, but I'm still in that first column. All right, and perform that 2 times 1 plus negative 1 times 1. And that gives me a value of 2 minus 1, so that is 1, a positive 1. Okay, and we see those are matching up right. Okay, and then here, now we have the third row, and again, still in that first column, so that we have 3 times 1 plus a negative 5 times 1, and that gives me negative 2. All right, and we see there we can continue. Now, once we've gone through the first, all 3 rows with that first column, I can move on here, and now I can focus here again, doing it one more time to get my second column in my product, where I'll do the rows again, but now I've moved on to the second column. All right, so doing that second column, we would have 1 times negative 1 plus negative 2 times negative 1. So that's 2 minus 1, so we get a positive 1. So that goes in there. And again, move on to the second row, still in that second column. So we get 2 times negative 1 plus negative 1 times negative 1, and we get 1. Positive 1 minus 2, excuse me, negative 1. Negative 1. Okay? And now moving on here, 3 negative 5, we get 3 times negative 1, and plus a negative 5 times a negative 1. So plus 5 minus 3 gives me a positive 2. Okay? And now I'm done with that second column in my matrix B. So I would go ahead and move on to the next one, right? And as you'll see, you'll get the same values as above, 8, 7, 21. And then here, 14, 13, 37, right? By just thinking of the rows times the columns, okay? Now here I inputted this in the symbol lab here, all right? And you'll see the solution here. You'll see at each step of the way here, you see they'll have the expanded version where we're doing exactly that, right? Row times column, right, at each element. And you see we arrive at the result that I arrived to as well. Okay, so that's another way, more compact way, more compact way to think of this multiplication here. All right, that is the equivalent to the way of thinking of the matrix vector product, right? That's the same operation that we're doing here.